So now I want to introduce the notion of a subset. So if we have two sets called A and B, every element of B is also an element of A, then B is a subset of A. So B is a set itself, and it is subordinate to A somehow. All of the things in B are also in A. So B is inside of A. So we will write this as B, let me write this nicely. It's like a smooth less than sign, like a little cup. So B is a subset of A. Or also you can say B is contained in A. Less common, but you may also hear it. A is a superset of B, which means that A is the bigger one. A contains B. So what are some examples? Every even integer is an integer. Which is, try to avoid saying things are obvious, but I hope this is obvious. And we can write that as our set of even integers. So we can write like this, is a subset of the set of all integers. That's what this is saying. Let's have more examples. So we introduced a bunch of different letters for the natural numbers and the integers, rational numbers, the real numbers, complex numbers. So these all have some containments between them. The natural numbers are contained in the integers, right? Because the natural numbers are essentially the non-negative integers. So 0, 1, 2, 3, etc., instead of also containing negatives. And the rational numbers are contained in the integers because every integer can be written as a fraction, just itself over 1. And the rational numbers are contained in real numbers. The real numbers are contained in the complex numbers. So we have a bunch of containments like this. Also, some more kind of edge cases, technicalities. Every set is a subset of itself, and the empty set is a subset of every set. So I want to make a quick notation remark. You will see these three symbols, subset equal to, subset, and subset not equal to. And this one, well, I'm going to tell you what I will use it to mean, but I just want to warn you that not everyone uses it this way. So what we mean by these is subset or equal. And this one means subset not equal. And other people will occasionally put this in that category, but I will not. So this is the notation that I will use. So if you want to say something that is a subset is not the full set, you got to specify that with the little slash. So that's a little comment on this containment. What about this one? So this, let's check this real fast, just to be precise. What do we need to check to show that this is a subset? If X is an element of the empty set, then X is an element of the integers. So this part, it's always false. The empty set has no elements. And what do we know about false implies anything? That is always a true proposition, right? So this is an example of the thing we were talking about as vacuously true. Now, maybe this is obvious, but I just want to say it anyway. Two sets are equal if they have exactly the same elements. Or equivalently, we can also write this as they are both contained in each other. So if A is a subset of B and B is a subset of A, then they are equal. And this won't always be obvious. So this example might not be too non-obvious, but maybe let's just write it down as a quick example. Let's use this set builder notation. Take the elements of the real numbers such that n times x is an integer for some n an integer. So these are elements of the real numbers that you can multiply by an integer to get an integer. What set is this? Claim that it is equal to the rational numbers. So let's check this. And often you'll find that checking equality of sets corresponds, comes down to checking these two things. So we'll check both directions. So I'm going to do, which one should we do first? Let's do left to right first. So I'm saying this thing is contained in this thing. So let X be an element of R such that n times X, let me give this a name, convenience, because I'm going to use it. Let's call this M as an integer. And n in this equation is also an integer. So rearranging this just a little bit, we get x equals m over n, where these things are both integers. And that tells us that x is a rational number, right? Because remember that the rational numbers are exactly numbers of the form one integer divided by another integer. And just keep reminding, in case everything's too unfamiliar today, this means contained in, it means it's an element. So x is an element of this thing, the rational numbers. All right, that's one direction. Or maybe let me be a little bit more explicit, just to dwell on this a little bit, make sure it makes sense. We showed that this side is contained in that side by choosing an arbitrary element of this set and showing that it is contained in this set. So that shows that this whole set is contained in that set. Okay, that is the idea. So the other direction, we do the same thing, or the same idea. So let's take an arbitrary rational number. We can write it as a fraction, because that is how rational numbers are written. Then, in particular, we can write it as a fraction where s is an integer. And also, s times x is r, which is also an integer. So s is an element, x is in, let me write the left-hand side, right-hand side. Which one's which? This is left. This is right. X is an element of the left-hand side. I'm just writing this to not have to rewrite all of that notation. But what am I saying? I'm saying x is an element of this set, which means x is a real number satisfying this property. And do we know that? So x is a rational number. So in particular, it is a real number. And we have checked that x times an integer is an integer, which is the property that we need. So it is indeed contained in the set. Okay, so that completes our checking. So this is what it means for two sets to be equal.